Hello everyone and welcome to chapter 12. Chapter 12 is actually called kinematics of a particle. So let us get started and look at the different terms. First, I would like to tackle the difference between kinematics and kinetics, as both of these terms are really important for this course. Kinematics is defined as the geometric aspects of motion. So it actually answers the question, how does it move? So we're actually after the terms speed, displacement, and acceleration. Those are the terms we're actually after. Kinetics, on the other hand, actually deals with the forces that cause motion. So when comparing kinematics to kinetics, one should remember that kinematics only focuses on motion itself. So we're interested in the parameters like speed, displacement, and acceleration, where kinetics actually looks at the prerequisites. So what are the drivers that are causing such a motion? And we're primarily dealing with forces. So we want to know which forces are causing a particular acceleration. So if you want to look at an example that deals with kinetics, let us imagine that we have a box standing on the ground, and I just put my finger onto that box and push it a couple of meters. Now the force that I applied with my finger is the main cause of motion, and that's what we're actually after when dealing with kinetics. This chapter only deals with kinematics. We'll talk about kinetics in the next section. Another thing to clarify is the difference between a particle and a rigid body, as you'll see both of these terms in this course. The first two chapters will deal with a particle, while the last chapters will focus more on a rigid body. So it is important to understand the difference between these two representations. A particle is basically an object that has a mass, but negligible size and shape. So here geometry is not involved at all. We do not care about the geometry of the object. We simply analyze it as a point, as a particle. So the object is said to be represented by a point mass. So the overall mass of the object is assumed to be located at the center of gravity of that object. On the other hand, a rigid body has a mass and a well-defined geometry. So you can think of a rigid body as a table or a box. They have a well-defined geometry. And so the mass is distributed along the width, length, and height of the object. So the mass is not only located at the center of gravity, it is actually distributed around the object. Now note that this representation is more complicated, but more realistic. So you can have better approximations when analyzing your problem. Now, if you want to see a visual representation of what a rigid body and a particle is, you can look at the image here on the right. So you can see a box which lies on the ground. You know that the box has a certain width, a certain length, and a certain height. And so the mass of this box is actually distributed among this box. So it's not located at the center of gravity, which is here drawn in red. On the other hand, if we assume a particle representation of that box, it would simply be a point, which is exactly the same as the point located at the center of gravity of the box. And we assume that the overall mass of the box, let's say 2 kilograms, is actually located at that center and not distributed. Another difference between a rigid body and a particle is the fact that the rotations of the body are completely neglected in a particle. Since you do not have a geometry, you do not expect the particle to rotate in any way. While a box can clearly rotate in 3 different axes, right? It can yaw, it can pitch, and it can roll. But let's not focus much on rigid bodies now, since our main focus is on particles. So to summarize, we'll actually work on particles, which are a simplified representation of rigid bodies. Now let us look at what kinematics actually is. So first I want to deal with rectilinear motion. And by rectilinear motion, we actually talk about a straight line. So we assume that an object can only move in a one-dimensional space. So kinematics is the analysis which is characterized by specifying at any given instant the particle's position, velocity, and acceleration. So those are the 3 main parameters we're after when doing a kinematics analysis. So let us start first by describing what a position is in a strict sense. So position is generally defined as a vector, so it has a direction and a magnitude. So if you look here on the image which is on the right, you can see that the object, which is highlighted in red, takes a position S1 first, then another position S2. And so S1 and S2 are basically the positions of the object. And to define a position, we need a magnitude and a direction. But as you can see here, since we're dealing with a one-dimensional space, there is no need for a direction, since the direction has to fall within that line. So when dealing with 1D representations, the magnitude is the most important parameter of a position. And the magnitude here is either S1 for the first position or S2 for the second position. Now that we have defined what position is, we can move on and define what displacement is. And it's actually defined as the change in position. So when you subtract the second position from the first position, that's the displacement of the object from state 1 to state 2. Now it is important to remember the difference between the distance traveled and the displacement. I have seen lots of students that actually confuse both of the terms and assume that they actually mean the same thing, but that's not true. The distance traveled is a positive scalar, so here we're not talking about a vector anymore, but only a scalar, and it is always positive. And it is equal to the total path traveled, while the displacement is only equal to the difference between two positions. So if you remember from the previous discussion, the displacement is only the difference between position 2 and position 1 in the image above. Now let us take a more complicated example and let us assume that the object highlighted in red actually moves past position 2, then goes back to it. And now you're asked to identify the distance traveled and the displacement. And you can notice that the distance traveled is actually larger than the displacement, since if you take the displacement between state 2 and state 1, you'll exactly get the same answer as the previous image. But if you analyze the distance traveled here is larger, since the particle has moved past state 2 and then came back to it. So this is very important to keep in mind. We have seen what displacement is and what position is. Let us now look at the velocity. The average velocity is defined as the displacement over time. So we can write V average is equal to delta S over delta T. So let us look at the example here on the right. Let us assume that the particle moved from position 1 to position 2, starting with an initial velocity, which increases and then decreases back until it gets to state 2. The average velocity is simply taking all that displacement, delta x, and dividing it by the total time, which is delta t. This would give you an average velocity. Now, if you want to know the actual velocity at every instant in time, we can simply take the limit as delta t goes to 0. So a visual representation of that limit is by simply shrinking this interval. So if we shrink the delta t on the schematic, this will decrease until it gets to a single point, and this would give us the instantaneous velocity. And remember, whenever delta t tends to 0, we actually talk about differentials. So one can write that v is equal to ds over dt. That's the instantaneous velocity. Now what about the sign of v? We're interested in knowing when v is positive and when v is negative. As you can see from the expression, we know that v is equal to limit of delta s over delta t, and we know that delta t is always positive. So the sign of v is dependent on the sign of delta s. So one can say that when going backward, the velocity is negative, and when going forward, the velocity is positive. So one can conclude that the sign of v is directly related to the direction of motion. So based on the motion, one can know if the velocity is positive or negative. If you're moving forward, the velocity must be positive. If you're moving backward, the velocity must be negative. It is also of interest to define another term, which is called average speed. And note that there's a huge difference between average velocity and average speed. The average speed is defined as the total path traveled, st, divided by delta t. And if you remember from what we've said before, the distance traveled is different from the displacement. And one great example is the one we've shown before. So the distance can be larger, but the displacement is only the difference between position 2 and position 1, regardless of the path that has been taken. Now, concerning the acceleration The average acceleration can be defined as the ratio of the difference in velocity by the difference in time. And so if we want to take the limit of this expression, exactly as we did before for the velocity, we'll get a value for the instantaneous acceleration, which is a, and it's the limit as delta t goes to 0 of delta v over delta t. And since delta as it goes to 0 is a differential, so we can write dv over dt. So we know that a is equal to dv over dt. Now remembering that we have an expression for v that is related to the displacement, v equals to ds over t, we can write an expression for a in terms of s, and that's a equals to d2s over dt2. And this means that a is the second derivative of the displacement. Now I want you to notice that the 2 is written after the d in the numerator and after the t in the denominator. And that's important. Now what about the sign of a? We're also interested in understanding how the sign of a translates visually. So we want to understand what actually means to have a positive a or a negative a. So if a is positive, you might already know that the velocity will be increasing. So if let's say a is equal to 1 meter per second square, it means that every second the velocity would increase by 1. And if a is negative, then the velocity is decreasing. And so if the velocity was, let's say, 5 meters per second, and the acceleration is equal to minus 2 meters per second squared, it means that as time passes by, the velocity will start decreasing and decreasing. Now we've previously said that the sign of v is related to the direction of motion. Now what about the sign of a? How is it related to the direction of motion here? So we want to see how acceleration and the direction of motion are related. So let us look at 3 different phases in a specific problem. So let's assume an object, which is here highlighted in red, moves in phase 1 with an acceleration of 2 meters per second squared, an initial velocity of 0 for 3 seconds. And then it moves to phase 2, in which the acceleration is now negative, equal to minus 0.5 meters per second squared, and for a delta t also equals to 3 seconds. Now finally in phase 3, the acceleration is equal to 0, and so the particle moves at the same velocity it was before for delta t equals to 1 second. So by analyzing the behavior of the particle here, we can notice a couple of things. First, the acceleration sign is not related at all to the direction of motion. So when moving from phase 1 to phase 2, the particle has already a certain velocity, which is positive, and it is moving forward, right? Because we've said that if velocity is positive, then the particle is moving forward. Now the acceleration is negative, but the particle is still moving forward since its velocity is still positive. So the acceleration sign has nothing to do with the direction of motion. Another thing to note is the fact that the acceleration can be non-zero when the velocity is equal to 0. And that's observable in the very first phase. So you have an object that's not moving yet, but it has to have a certain acceleration first for its velocity to start increasing and for it to move. So an acceleration can be non-zero when the velocity is equal to 0. It does not have to be equal to 0 as well. And that's very important to remember. Finally, I would like to discuss the equation of motion that is independent of time. In order to find this sort of expression, one needs to make use of the 2 first equations of motion we've covered. A equals to dv over dt and v is equal to ds over dt. Now as you can see, there's this dt term in both of the expressions. So one can write that dt is equal to dv over a and dt is equal to ds over v. And by combining those 2 expressions, we end up with an expression that is totally independent of time. And it says that dv over a is equal to ds over v. And now if we take the cross product, we'll end up with v dv is equal to a ds. Now one thing that's important to note is the fact that this equation is dependent on the 2 first equations. As you have seen, we're only able to derive this equation by using the 2 other equations. And so it means that it does not provide any additional information. So far we've seen 3 different equations. The first one is v equal to ds over dt. The second equation is a equals to dv over dt. And the third equation is v dv equals to a ds. Now those three equations are the fundamental equations of motion, and it actually means that all other equations that we'll see in the kinematics of any object, whether it's a particle or rigid body, are all derived from these simple equations. And the way we actually create new equation is simply by integration and replacement. So let's look at an example, an application of what I've just mentioned. So let us assume a constant acceleration process, which means that AC is equal to a constant. And now we're asked to develop expressions for velocity, acceleration, and position as a function of time. Now remember, we only have three equations at hand, and the only way we can derive new equation is by integration and replacement. So it is always good practice to start with what we know. So we know that the acceleration is constant, so one can write that A is equal to a constant is equal to AC. Now the way to move forward is to make use of an equation that includes the acceleration term. And the most logical equation or simple equation to use is A is equal to dv over dt, which will allow us to compute an expression for the velocity. So one can write that dv is equal to A dt. And then by taking the integration from both sides, one can write that integral from v0 to v of dv is equal to the integral from t0 to t a dt. And by doing the integration, one ends up with v going from v0 to v is equal to at. Since a is a constant, we can take it out of the integration. And integral of dt is equal to t from t0 to t. And then assuming that t0 is equal to 0, the main reference, we have v is equal to at plus v0. So we were able to derive an expression for the velocity, assuming a constant acceleration, by simply making use of one of the fundamental equations of motion. Now similarly, if we want to find an expression for the position or displacement, one needs to make use of the equation v is equal to ds over dt. Then doing the same procedure and applying the integration, one ends up with integral of s from s0 to s of ds is equal to the integral from t0 to t of v dt. Then here one needs to replace the value of v with its expression in terms of time, and that's at plus v0. And performing the integration, one ends up with the expression s minus s0 is equal to half at squared plus v0t. So that's another expression which describes the variation in position as a function of time. And finally, the third expression can be used to derive an expression that is independent of time. Remember, we have v dv is equal to ads. Similarly, performing the integration from both sides, one has v squared minus v0 squared is equal to 2a s minus s0. And as you can see in this expression, there is no reference to time. The only variables are the velocity, acceleration, and position. Now I like to sort of simplify the equations and summarize them by simply writing the different variables that make up this equation. So in the first equation, the one that relates velocity as a function of time, we have the velocity, the acceleration, and the time as variables. For the second equation, which is related to the displacement or the position, one has the velocity, the acceleration, the time, and the position as variables. And finally, for the third equation, there are only three different variables for the equation: the velocity, acceleration, and displacement. Now notice sometimes I use displacement and position interchangeably, but remember that they are quite different. The displacement is the change in velocity. So whenever you have a subtraction of two different positions, that's a displacement. And so that's why I actually use it interchangeably. Because if you look at the third equation, we have an s minus s0 term. So it means that the displacement is one variable. And the displacement is actually made out of two positional variables. So one can make use of position or displacement as a variable. Now I would like to talk about the chronological order of the different parameters. So one might wonder what comes first. Is it the acceleration, the velocity, or the displacement that comes first? Now to answer this question, one again needs to make use of the fundamental equations of motion. So one has v is equal to ds over dt, which means that ds is equal to v times dt, and by performing the integration, one has that s is equal to the integral of v dt plus s0. Similarly, doing the same thing for a equals dv over dt, one has that v is equal to the integral of a dt plus v0. Now, I would like you to think of the integral term as a sum of the velocity components. So one can say, assuming s0 is equal to 0, that for it to be a change in position, there needs to be some velocity first. So the v term has to be different than 0 first for it to have a change in the position. Similarly, looking at the second equation, one can say that for it to be a change in velocity, there needs to be some acceleration first. So assuming you have an object that's resting on the ground with a velocity of 0, and this box actually needs to have a certain acceleration first for the velocity to start increasing or decreasing, and so for the box to move. And so one can say that the acceleration comes chronologically before velocity, which comes before displacement. So in order to get a certain velocity, one needs to have an acceleration first. And once you have a certain velocity, you'd have a certain displacement. And so the terms follow this certain chronological order. Now, as you might already know, in engineering, we make use of lots of different graphs and plots to better understand the problem. So it is useful to understand the graphical way of representing the kinematics. So here we'll discuss the graphical analysis of the kinematics parameters such as speed, velocity, and acceleration. So let us start with a equals to dv over dt. So by looking at this term, one knows that a is the derivative of v with respect to time. And graphically speaking, the derivative is actually the slope of the function. So in this case, one can say that the acceleration at time t is the slope of the vt curve in a vt graph. So if you have the velocity which is being plotted as a function of time, taking the slope of the velocity curve at any instant would give us the instantaneous acceleration. Now, if we look at this expression in another way and write dv is equal to a dt and performing the integration, one has that v minus v0 is equal to integral a dt. And again, graphically speaking, the integral of a function is simply the area under the curve. And so in this case, one can say that the change in velocity, v minus v0, is equal to the area under a t curve in an AT diagram. So if you're given the variation of e as a function of time, the change in velocity is simply equal to the area between the reference point 1 and the reference point 2. Now doing the same for the second equation, v is equal to ds over dt, we can also write that s minus s0 is equal to the integral of v dt. And so we can come up with the same conclusions related to the velocity and the displacement. So in conclusion, one can say that the slope of the vt curve is the instant acceleration, the slope of the position curve, st, is the instant velocity, and the area under the AT curve is the change in velocity. Then finally, the area under the vt curve is the change in position. So these different statements were all obtained by simply making use of the derivative and the integral terms.